All right, so here's a quick tutorial video on growth rates. Really what this should say is it's applications of log and exponential equations. So like in our class, we just finished a section where we were learning how to solve exponential and logarithmic equations. And then your book follows up with, like a lot of books do, some real life applications of this stuff, which really amounts to a bunch of kind of contrived problems that end up giving you an equation that either has exponents or logs in it, and you solve that and you're good. And for the little bit skeptical, but for the purposes of our class, what we're going to do is either I'll just give you the equation, like the temperature of a cup of coffee is given by this equation, and then you're just solving an equation. And yeah, I guess it's technically an application because it's given in the context of a word problem, but really it's just a question from the previous section where you're given an equation and you're solving for something. The exception to that is this growth rate stuff. So with growth rate, there's a couple formulas you need to know, and those are provided for you right here. So there's going to be two different versions. Kind of here's one up here and two down here. And the key thing on this video is understanding when to use one formula versus the other and how to use one formula versus the other. So what you need to know is that in either case, the f of t tells you kind of how much of the thing, whatever you're talking about, you have at time t. So how much you have, or there is, at time t. And so as it kind of says here, the t in these equations, that's just going to be time. The a in the equations, and it's not always a, your book uses a, but some books use p naught or k or other variables here. But the a is the initial amount. And finally, the r is the growth rate. And you want to format the r, format it as a decimal. And I'll show you what I mean by that. Well, I guess I'll tell you what I mean by that. If it grows at 8%, you don't put an 8 in for r, you put 0.08 because 8% is a decimal, is 0.08. And note that that's if it grows by 8%. If it decreased by 8%, then it would be negative. So it's your growth rate. Therefore, if r is negative, it's a decrease. If the growth is negative, it's a decay rate, maybe. So these are what the different constants in these equations stand for, I guess in some case a variable. And really what you need to know is when to use one versus the other. And the key word is the word continuous, right? If your stuff can grow by a certain amount over a time period, so growth rate per period. So like, for example, you might see something grows by 8% each year. So in the end of one year, you have 8% more than what you had at the start of that year. It's growing by 8% per year. That's this growth rate formula here. A times something to the t power. You're like, oh, that looks kind of familiar. That looks a lot like, maybe I'll write this. Think y equals ab to the x. Kind of our general form of an exponential equation. Playing the role of b is this 1 plus r thing here. So if something grew by 8% per year, what we would say is that, well, I guess we need to know what a is. Maybe I won't go plugging this in. I'll save the examples for down here. The other option is if it's not a growth rate per period, but it's instead a continuous growth rate. So if something says, for example, this thing is growing at a continuous, that's kind of the key word here, continuous annual rate of 8%. That doesn't mean that after a year you have 8% more. It turns out that after a year you have a little bit more than 8% more, 8 point something. Actually, I don't know exactly what it is, but we'll be able to figure it out with these examples. So if you have a continuous growth rate of 8%, you end up with more than 8%, more than what you started with at the end of the year, which is a little bit counterintuitive, but the idea is since the growth rate is continuous, you're getting interest on the interest. Right? So not the initial amount grows by 8%, but like after a month, I have a little bit more than I started out with, and that little bit more is also growing for the remainder of the time. At any rate, two formulas, continuous is a keyword you're looking for. So let's do some examples to try to make that make a little bit more sense. So this first example says, if your $1,000 investment grows 8% per year, note that nothing about a continuous growth rate. This is an annual growth rate here. How long will it take for it to be worth $2,000? Okay, so how long will it take? Sounds like I'm solving for t. That's what I'm going to try to figure out. So I'll leave the t as a t. I'll note this top equation because it doesn't say anything about a continuous growth rate. So I got to plug in for everything except for t. F of t is how much I have at time t. At time t, it'll be worth $2,000. So I say 2,000 equals A. A, what was that? Oh, right, my initial amount. If your $1,000 investment, sounds like starting with $1,000. Grows 8% per year. So in my formula, it looks like I always have a 1 here, but then I got to put in R. And you're like, 8? No, 0.08, because remember R is supposed to be formatted as a decimal. And I want to raise that up to the T power. And you're like, what's T? And I'm like, what's T? You're supposed to figure out T. It's not given to you. You're supposed to solve this equation for T. If you think about what this equation is, this looks like something that could have been given to you in the log and exponential equation section. Right? It's an equation. You got to solve for a variable. Everything else is a number. You got to get this T by itself. How am I going to get this T by itself? It's up in the exponent. Oh, right. I got to introduce logs. Right? So really what I have here is 2,000 equals 1,000 times 1.08. That's 1 plus 0.08 to the T power. I want to get at this T, so I have to introduce logs, but this 1,000 here is going to get in the way if I try to take the log of both sides right now. So maybe I'll divide both sides by 1,000 first. If I do that, I get 2 equals 1.08 to the T power. So now to get this T, I got to take the log of both sides of the equation, whichever log you prefer. You just take a log base 5, log base whatever you want. I typically use natural logs, maybe just because it involves less letters. If 2 is the same as 1.08 to the T, then the natural log of 2 is the same as the natural log of 1.08 to the T power. How's that help me? What we refer to as our third log rule allows you to take this exponent, bring it down in front. So the natural log of 2 is equal to T times the natural log of 1.08. So now the T is not up in the exponent. That's awesome. Now I can solve for it. How do you solve for it? Well, it's T times something. So divide by this something. And you got T. You got T equals natural log of 2 divided by the natural log of 1.08. If you care what that is, I mean, I don't. But you throw this into a calculator and throw this into a calculator and figure out what it's equal to if you care. I don't know that I really care. You can express your answer as a decimal if you want. Or you can just leave it like this. I'm not so worried about you being able to punch this into a calculator. I'm going to call this good. This is T. This is some number. If you're curious, you can figure it out on your own. That's what T is equal to. That's how long it'll take. So really, if you think about what we just did here, the challenge is A, knowing which formula to use, B, knowing how to plug in everything in the formula, and then C, solving for T. And really, only C is the thing that we're learning new in this class. And you've seen formulas before, and you've plugged in numbers before. But solving this for T is a little bit challenging because the T is up in the exponent. And so you got to use this new trick that you just learned, where you take the log of both sides of the equation to get at this T that's up in the exponent. Let's do another one, get a little more practice. What is the half-life of an element? So first off, you need to know what the half-life of an element is. This is defined to be the amount of time. So this is a T. It takes to decay to 1/2 the initial amount. What do we know about this element? It decays continuously. Right? That's the important word that you see when you're reading this. It tells you using this second formula, not this first formula, because this deals with continuous growth rates. So we're trying to figure out that we're going to try to use this second formula here, that f of t equals a e to the RT power. But there's some challenges here, right? You're like, f of t, that's how much I have at time t, and a is how much I start out with. It doesn't tell me either of those things in this problem. And the reason it doesn't tell you them is because you don't need them. When you're figuring out the half-life, you can start out with whatever you want. It doesn't matter what the initial amount is, because the half-life is defined to be the amount of time it takes to decay to half the initial amount. So start out with 100, fine, then this is 50. Start out with 1,000, fine, this is 500. Start out with 16, then this is 8. You just want to set this to half of whatever you make this. Doesn't matter at all what it is, right? Maybe I start out with 100, because why not? And then what I have to do is set this to half of that amount, because I'm trying to solve for the time that it'll take for some amount, whatever the hell amount you want, to decay to half of that amount. And what you'll see in just a second is it doesn't matter at all what you put here. So I'm putting in 100 as kind of a placeholder. As long as this is half of this, you're good. What about the rest of my formula? I got an R and a T. R, what was that? Something about rate. Oh, right, the continuous growth rate at 5%, formatted as a decimal. So I want R to be 0.05. Note that up here, I had an 8% growth rate, and that turned into 1.08. Whereas here I have a 5% decay rate, That's not going to turn into 1.05. It's going to turn into 0.05, right? Because my formula is just an r here, not a 1 plus r. Furthermore, because this is a growth rate, r is positive. Because this is a decay rate, r is negative. So this tells me that r is equal to negative 0.05. And what I got to solve for is t, right? I'm trying to figure out the half-life. The half-life is the amount of time. It is at. So we say this is e to the negative 0.05 t. Solve this equation for t. How am I going to solve this equation for t? T's up in the exponent. Oh, right. I just did that up here. Right? You want to solve for t, you're going to take a log of both sides. I'd recommend natural log because the base is an e here. But before you do this, you want to deal with this 100. And so maybe I divide both sides of the equation by 100. And note that I'll get a 1/2 over here, e to the negative 0.05 t. Before I continue, suppose you started with 80 instead of 100. Then you would have made this 40. And your first step would have been to divide both sides by 80. And instead of 50 over 100 equaling 1/2, you would have had 40 over 80 equals 100, or equals 1/2. Start with whatever the hell you want, as long as this is half of that. In your first step, when you divide those two numbers, you'll end up with a 1/2 right here. So you could argue that it would make the most sense to start with 1 and set this equal to 1/2, so that I start out at this step. And yeah, absolutely, that's a good way to go. But just so you understand why you can start with 1, I wanted to do this example. Now solve for t. Well, it's easier than up here because my base is e. I can take the natural log of both sides, and I get that the natural log, I guess here, of 1/2 is equal to the natural log of e raised up to the negative 0.05 t. And you're like, wait a minute, let me write. I can't write and talk at the same time, which is bad if you're trying to make a video. You might be thinking the natural log of e raised up to this power. Doesn't the natural log and the e kind of sort of cancel out and just this turns into negative 0.05 t? Yeah, absolutely. Because you can use your third log rule like we did up here to take the exponent and bring it down in front. So I can take this exponent and bring it down in front and get negative 0.05 t times the natural log of e. And the natural log of e, the natural log means the log base e. So the natural log of e is asking you the question, what power do you have to raise e up to make it equal to e? Well, e to the first power equals e, so the natural log of e equals 1. What I'm saying is this whole thing's all gone. So my equation looks like this. So get the t by itself. How? Divide both sides by negative 0.05. I get t equals the natural log of 1/2 divided by negative 0.05. I am of the opinion that it looks a little bit weird to have a negative in the denominator. It's not incorrect, but often you'll see this written maybe more like this. And you're like, whoa, t's negative. Something's wrong. I screwed this up. Time can't be negative. I mean, at least in this context. Natural log of 1/2 is a negative number also. So this fraction in here is negative, and the negative of that negative, this is actually positive. Don't believe me? Go punch this into a calculator. That'll tell you t. I don't want to spend the time to punch it into a calculator. I will call this answer right here perfectly good. And I move on. One more, just to kind of round things out. Maybe I'll switch colors so they don't run together too much. Third question here. What is the continuous daily rate of decay for an element with a half-life of 20 days? So this one's a little bit different, I guess, although what you'll see is it's almost the same. First thing is continuous. I'm looking for a continuous rate. Oh, right, that's that key word. That tells me I'm using the second formula and not the first formula. The element has a half-life of 20 days, so I can pretend that I'm starting out with 1 and I'm ending up with 1/2 after 20 days. Right? I'm sort of taking this formula right here and plugging in 1/2 for f of t, plugging in 1 for a, but 1 times something. You don't even need to write that 1 that's a. And then I'm leaving room up here for r times t. What do I plug in for r? Plug in r for r because it's asking you what is the rate. You're supposed to solve this equation for r. That's kind of weird looking. Well, yeah, you could rewrite it as 1/2 equals e to the 20r power because r times 20 is 20r. And then solve this equation. Up here we had to solve for t. Down here we're solving for r, but it's the exact same thing. Right? We have 1/2 equals e to some power. Just like I did here, we got to get that power out of the exponent and then isolate the variable. So we take the natural log of both sides. Get natural log of 1/2 equals the natural log of e raised up to the 20r power. And then either in one step or in 2 steps, however you feel good about doing this, you realize that that right-hand side is really just 20r. So to get r, I'm going to divide both sides by 20 and call this the natural log of a half divided by 20. Same thing, if you want to know what number that is, go ahead and plug it in. It's fine. Put it into a calculator. I don't care what number it is. Comment here is that, okay, I would give you full credit if you left this as your answer. But the natural log of 1/2, that's a negative number. Maybe I'll pull up I don't know if I want to do this. Sure, why not? I'm going to calculator, natural log of 1/2. See what Google can do for me. It's negative 0.693. Right, so roughly negative 0.7, maybe if I'm really rounding these off. So this is negative, what did I say, 0.7? Hopefully that's what I said, over 20, which is equal to, let's take that answer and divide it by 20. Well, let me just do that. Maybe divided by, yeah, well, how cool. Go ahead, Google. Gives me this, negative 0.035, I guess, if I'm rounding this. Negative 0.035. I think I can remember that for a couple of seconds. Negative 0.035, roughly speaking. What is this saying? Why is this negative? It's because this is a rate of decay. Right? So if you remember up here in this formula, R is your growth rate. If it's positive, it's how much I'm growing by. I'm not growing, I'm decaying. That's why this is negative. This question asks you, what is your rate of decay? So it's decaying at roughly, 3.5%, or it's growing at negative 3.5%. So kind of getting into semantics here, and I don't really care a whole lot about these, but I just figured I should make that point just so you can see when it's negative, it's decaying. So technically the answer to this question, I guess, is what would be the positive 3.5. Why? Because it's asking for the rate of decay. It's not asking for the rate of growth. If it asked for the rate of growth, it would be negative 3.5. Anyways, I don't want to get too caught up in the details. What I really want you to learn here is that there are two new formulas that you're going to want to understand, memorize, if you will. And this one deals with when you have a continuous growth rate, and this one deals when you do not have a continuous growth rate. And typically, in order to make these interesting, you'll be solving for something that's up in the exponent. Not always, but because the idea of these applications is to build on what you learned when we had logarithmic and exponential equations, I kind of want to involve some of the techniques of solving logarithmic and exponential equations, which was introducing logs. So typically it's one of these variables up here you're solving for. So either the t in this case, or the r, or the t in this case, which is exactly what we did in these three examples. So I think that's all I got. Hope that makes sense, people. I will see you on Monday. No, I won't. I'll see you on Wednesday.